Awesome. Welcome everyone to the Torch-MLIR community meeting for the month of August. Today, we're going to be having some workload updates from Anush. Alessandro from AMD will be presenting on some of his work using running quantized models using Brevitas. And lastly, we'll have an update from Stella and Sean towards the end. But before we get to that, a few reminders. So this is the community meeting for Torch-MLIR. It happens on the first Monday of every month at 9 a.m. And it sort of has, the major updates of what's happening in Torch-MLIR, and usually a presentation of interesting use cases of Torch-MLIR. We also have the developer hour every other Monday at the same time. And that's more for technical discussions. It's not recorded. There's no agenda. So if you have any questions, feel free to drop by during the developer hour. There's also office hours every Thursday from 8:30 to 9:30 a.m. That one is hosted by me, and it's more for entry-level questions or help with debugging and things like that. Lastly, we have a very active Discord. So if you want to stay up to date with the latest news in Torch-MLIR, that would be the place to do that and to also ask questions. And there's also a discourse on LVM. So in the last, so we didn't have a community meeting last month because it was a holiday. So in the last 64 days, we had 82 commits in total from a variety of contributors. So thank you all for all the work you've been putting in. There's been a lot of work on the ops, a lot of improved ops, which means bug fixes, but also improving the edge cases that are supported in each of the ops. So thank you everyone who worked on that. And with that, I will pass it on to Anush to give us some workload updates.
Thanks, Amiro. So I think from the workload updates, we're just continuing to build out on the LLM models. We do have Llama 2, which came out recently, and I think Beluga is Llama 2 trained with the latest thing. And it may have been superseded already today or in the last couple of days. I think Upstage is the latest one, but Llama 2 is functional, so that's a good starting point. We're trying to maintain a sort of like SLA of like a day or two once something hits the OpenLLM leaderboard. So if there's anything that comes up, we want it to be automatically supported through Torch-MLIR down to all the various backends. We do have code gen also. I think there's also a Llama derivative, but for coding assistance. So we have both of those included in Shark, and it can work with like your VS Code plugin for autocomplete. It's good to see like an end-to-end workflow and everything running through Torch-MLIR. We do have Stable Diffusion XL as a whip. I think there are probably another day or two before we land that for production. We do have H2O GPT, which is Falcon 40B plus all creating the vector databases and being able to query local documents. So you can point it to a directory with local documents and be able to chat like an LLM. So those have been primarily our focus. We have a few others that are in the pipeline for the next few weeks that should be coming up. Cool. Any questions? And on the, tying to Alessandro's thing, but we also have Llama with GPTQ quantized running through Shark, through Brevitas. So we have int 8 fully validated. Int 4 is mostly there. There's still a few more tweaks here and there that we have to do for the code gen side, not on the lowering side, but on the code gen side. But I think this week we should be able to have a viable alternative to Llama CPP, so that you have like a solid Hugging Face entry point. Use the models quantized with Brevitas, passed to with Torch-MLIR, and then code gen with Eevee and deployed on multiple hardware. Cool. Any questions, folks? Okay, back to you, Ramiro.
Awesome. Yeah, thank you so much for that. And with that, I'll pass it on to Alessandro to give us his presentation.
Hi, everyone. So I'm Alessandro Pappalardo. I'm from AMD Research and Advanced Development, we're called these days, which is the new organization that resulted from the merging of the classic AMD Research Org and the Xilinx Research Org, since I come from the Xilinx part of things, and we got acquired last year. I'm going to be talking about some of the work that I've been doing, especially with Anush and these folks on this LLM quantization, especially with GPTQ, through this quantization library that I've been working on for the past few years at this point, called Brevitas. So Brevitas is a PyTorch library. It's open source. It's mostly, I would say, mostly all PyTorch code for neural network quantization. Originally, something I was working on at Xilinx Research, and now at AMD after the acquisition. When I say quantization library, what that means is that Brevitas simulates the effect of quantization error. That is the typical thing whenever you hear about libraries doing quantization, that it actually means, in the sense that you try to account for the error introduced by quantization at framework time, where you have a lot of tools to basically try to potentially compensate for that, whether it's with post-training quantization algorithm or quantization-aware training, where post-training quantization usually means that you introduce quantization after, let's say, training has been done, or the vast majority of training has been done, and you just first introduce quantization and then try to adjust for the error introduced by that. Or quantization-aware training means that you are basically simulating quantization error as part of your training loop, and thus incorporating the error from quantization as part of your overall loss function. So Brevitas gives you tools to do all these sort of things as well, different PTQ algorithms, QAT algorithms, different ways to integrate it with your larger training flow, or or whatever it is. And I won't get into the details of that because I don't think it's necessarily as relevant to this audience, but I'll just mention that, yeah, you can use it for all sorts of concern. I'm just going to present a slice of what you can do with this talk. And in particular, when it comes to acceleration, Brevitas doesn't do any acceleration per se. But instead that is offloaded to some third-party backend that we communicate with through some explicit intermediate representation. So there is an export step. And typically that would be to either a non-Next-based IR or a TorchScript-based IR. And with TorchScript, we have historically at least like a good entry point into the Torch-MLIR ecosystem. And so this is what I'm leveraging in this context, basically. And by the way, yeah, feel free to stop me if you want to say anything or comment, question. They're always welcome. And so the weight-only quantization scenario, I would say it wasn't so popular until recently, in the sense that historically, quantization has always been applied more to these CNN type of models, if you are, if you're familiar with this field, where things are typically compute bound, and so you take advantage of quantization to reduce basically the width of the compute that you are operating over, to do things like in-tail compute or in-for compute. But with the explosion of larger generative models, the weight quantization paradigm has started to become much more relevant than it was in the past, for two reasons. I would say one is to reduce model size, since most frameworks don't operate really well in a highly heterogeneous memory hierarchy. It's always easier if you can fit your whole model in, say, GPU RAM. It does make a lot of difference if you can fit an entire LLM within all of your GPU memory, and so quantization plays a role in that. And the second reason is obviously then for speed up reasons, which are not necessarily guaranteed, but with quantization, you enable the opportunity at least to gain a speed up on any sort of workload that is bound on weight bandwidth, like LLMs at least typically are, so especially on the decoder side, as an LLM is. And the way to do so is to basically take these low precision weights and unpack them to higher precision so that they can be used then for the actual compute part, which is typically some, high precision floating point format, and with high precision, I mean either 16-bit or a 32-bit format. And to take advantage of the bandwidth savings, obviously you need to do this unpacking as close as possible to the high level of your memory hierarchy, let's say, so in registers or something equivalent, depending on the architecture. So the GPTQ algorithm, there's anything that I want people to take away from this presentation is probably this slide. You hear a lot about GPTQ and GPTQ quantization. The point that I would like to make is that there isn't any GPTQ quantization per se, in the sense that GPTQ is a post-training quantization algorithm that is designed to compensate for weight quantization error. And if you look at the original publication that is also linked below, you will see that in the formula of the algorithm, which is the thing that I'm showing here, there is no actual dependency on any specifics of how the weight quantization is done. So in principle, you can apply GPTQ on top of any style of weight quantization, whether it's uniform, non-uniform, or per channel, per tensor, whatever. So this is just to say that in principle, even with the degree of weight quantization that was already supported in existing tool chains, you could have applied the GPTQ to that already. However, things have sort of evolved in a different direction, at least in the literature and the community, and I'm going to show that in a second. So talking about weight quantization, the typical way that you would normally do it in the context of deep learning is to do uniform weight quantization. This comes historically from the fact that with weight quantization, typically you would also do activation quantization, and the moment that they're both quantized linearly, they're very easy to accelerate. When you do weight-only quantization, this is not so much of a requirement, to be honest, and this is why these sort of non-linear quantization schemes have also started to emerge. But I will say the most popular way to do it is still the uniform affine paradigm, where basically you're just, quantizing value to an equispaced grid of integers. And you do that with some scale factor that basically represents to which value you're mapping integer 1. And you might do it also with a 0 point, which represents by how much basically you want to shift your quantization range, so your 0 in practice across the x-axis basically. And but it's not as much as a requirement. The main requirement is scaling when it comes to integer quantization, and optionally also a 0 point. And you find that the scale is you have these metrics of integer values for the weights, plus a scale that is going to be a float 16 or a float 32 value typically, plus a 0 point is going to be either an integer, typically quantized to the same precision as the rest of the tensor, or a float 16 or float 32 value, although that's not something that I suggest because it can more easily introduce errors. And talking about granularity, and then wrapping it back about my point on GPTQ, the idea is that you can have different degrees of granularities for scales and 0 point. The bigger the scale and 0 point is in terms of tensor rank, the more fine-grained your quantization is, so the higher the quality of your quantization. At the same time, you also pay a higher cost in terms of potentially storage and compute. The two typical historical paradigms, I would say, that were very common on the CNN side are tensor-wise quantization and channel-wise quantization, where in the past, what you have done is say tensor-wise quantization on activations and channel-wise quantization on weights. And this type of quantization is very effective whenever you also have activation quantization, because it allows enough degree of decompositions among all the different tensors such that all the scaling and all the 0 points can be handled after your arithmetic, like your integer arithmetic. But when you want to do only weight-only quantization, you're not as much concerned with how the quantization granularity is going to affect your compute structure, because at the end of the day, the compute is always in floating point anyway. And so you can afford to get a bit more creative. And this is why I would say, we've seen the emergence of all these more fine-grained quantization schemes, and in particular, group-wise quantization has become very popular, where basically you just say that every certain number of value, you are assigning, a scale factor and a 0 point. And this obviously provides very high quality, fine-grained quantization. The one that has become very popular, combined with GPTQ, I would say, is with group size 128. So if you look out at these, repositories on GPTQ, or also on the literature on the topic, they all tend to align on the idea of doing a group-wise quantization with group equal to 128. But I hope my point is made that in principle, GPTQ per se is just a post-training quantization algorithm that can be applied to any of these various constraints. That said, the one that we care about in this context is the group-wise one, since it's the one that gives the highest quality, and it's the one that we are currently deploying. And so talking about the LLM flow that I've been working on, it's a work in progress. I would say, everything is always a work in progress. Currently on the dev branch of Brevitas, it was originally designed based on the code that came out from the GPTQ paper, generalized sort of on top of Brevitas API for quantization. So it's mainly tested with Llama 1 currently, as well as OPT, which is another model family that we care about for activation quantization mainly, actually. I support a variety of different quantization styles, so not just group-wise, but there's also, per channel, per tensor. There's also activation quantization if you want to do that with static or dynamic scale factors with different granularity. It's all designed basically to be able to experiment with how different styles of quantization can impact the overall perplexity of the model. And at the same time, to also provide an entry point for deployment for certain combination of configuration when it comes to how quantization is done, as well as which GPTQ algorithms are applied. And I support a few. There's GPTQ, which is to improve on the quality of weight-only quantization. There's MoodQuant, which is to improve on the quality of activation quantization. And there's also some support for AWQ, which is another algorithm from Song Han Group to improve on the quality of weight quantization. There is export to various IR. Obviously, Torch-MLIR is one of them. However, the point I would like to make is that this design space is fairly wide in terms of all the different quantization options that you can plug in. And unfortunately, not every IR supports every combination of quantization styles. And it's a matter of whether, there's some pre-existing operator that I can target to represent whatever style of quantization I'm applying, or if there isn't, whether I have some custom op to capture what I'm doing or not. The good thing is that at least in Brevitas, it's very easy. If you care about lowering to a target IR and you don't have an op to target, it's very easy to plug in some custom symbolic representation. And this is basically what we do in this case for the weight-only group-wise quantization. So the way that the flow works is the following. We start with some model loaded from Hugging Face, and typically Hugging Face models, they rely on standard Torch linear layers coming from upstream PyTorch. So we have a simple flow to just replace those with Brevitas quant linear layers, which represent our abstraction for quantized linear layers that can then be parameterized with different type of quantization styles, like I was describing before, depending on what you're interested in exploring. In this case, we're interested in doing a group-wise quantization. After we do that, we call the GPTQ implementation in Brevitas. So Brevitas has its own GPTQ implementation that works on top of Brevitas API, and that's used basically to as the GPTQ algorithm does, to reduce the amount of quantization error that is introduced by weight quantization by tuning the underlying weight value that is being quantized. After that's done, what happens is that within Brevitas, we replace the standard forward pass of the quant-linear layer with a custom symbolic representation that captures the specifics of the quantization that we're doing. And this is something that is overlaid, I would say, on top of quant-linear, and is designed basically to capture different type of ops that then we want to sort of lower in a particular IR. And so in this case, what we're doing is that we're plugging in this custom symbolic representation, where with symbolic, I mean an operation that doesn't come with an implementation per se, but only comes with information how to propagate shapes and how to propagate the types. And then this custom symbolic operation is traced. And we are using MakeFX to perform a tracing, which is, as far as I understand, the suggested approach to do things currently in Torch-MLIR. And MakeFX, as part of its tracing process, at some point it's going to encounter the symbolic op on the forward pass of quant-linear, and it's going to preserve that as part of the export trace. And then this, this generated FX graph can be passed to Torch-MLIR, and currently that is internally by lowering to TOLScript. Something that we also do, sorry that I haven't mentioned, but it's on the slide, is that as part of this export process, during this forward pass replacement, we also do some pre-processing to do any sort of pre-processing operation that might be necessary to prepare for export. And one of the main things in this case is to do packing of these quantized values from their original wider container, which might be, FP32, because during the quantization process, weights are still represented as FP32, packed into now, since we're doing, say, int4 quantization, we're going to pack to int4 values every one, int8 value. And yeah, and so that's basically it. There isn't, honestly, at least at a high level, there isn't too much other than that. However, I would say there are a few outstanding issues currently. So the main one is with the MakeFX itself, unfortunately. Torch-MLIR, as far as I understand, currently leverages MakeFX mainly for op decomposition, since MakeFX provides this infrastructure to decompose ops that aren't yet supported by a downstream compiler into a sequence of simpler operations that instead are supported. And it's also useful if you want to do any sort of transformation on top of the the graph IR once it's generated. For example, I've seen that being done to handle casting to FP16 whenever you are doing the tracing on CPU, since CPUs normally cannot do FP16 tracing, at least in PyTorch. The problem is that at least upstream MakeFX doesn't respect these wrap annotations that you would normally use in the context of effects to basically encapsulate custom ops and make sure that they are not traced through during the tracing process, and instead preserved as is, which is what we want to do in this context, especially because with a symbolic opt, there is an actual implementation associated to it. So we just want the symbolic opt to be captured as is as part of the export, exported graph. And so what I'm currently doing basically is that I have a whole backport of effects in Brevitas, which is not great. I had that in the past actually as a sort of uniform surface to implement custom tracers across different versions of PyTorch. Originally, I was going to deprecate it, but now it became necessary again also for these use cases. And basically what I'm doing is that I'm just backported MakeFX from PyTorch 2.0.1 down to up to 1.12, I think. And on top of that, I've merged a proposed PR that was in PyTorch that is currently, fortunately, stale, on how to basically modify the MakeFX implementation plus some of the underlying effects IR to address this issue. Long term, what would be nice is to switch to this new proposed capture API that is being discussed upstream in PyTorch, to basically unify different functionalities on how custom ops should be captured across different lowering flows. Unfortunately, it's a very complex topic, and I've noticed that it's not progressing so much. So it would be nice also, I guess, as a community, if we could make sure that at least this previous Stella PR that addressed the issue for MakeFX is merged in, so that we don't necessarily have to rely on my own backport. But at least, I mean, the backport is there, so it can be used. The other thing, and this is more up for debate, I guess, is the fact that right now, what is being generated as a custom op is this custom matmul operator with right-hand side group quantization. That's how I called it, and hopefully gives the idea of what it's doing, which is group-wise quantization on the right-hand side, so the weight side of things. The reason why I don't love this in a way is that it already encapsulates the fact that the quantization part and the matmul part are supposed to be fused. And unfortunately, I would say capturing any sort of fusion patterns at the level of the quantizer with a tracing-based flow is not necessarily very flexible. And in particular, it also makes it more difficult to then generalize to other ops whenever it's not going to be matmul, but it's going to be something else. It means that I just need to have a lot of different combination of these custom ops. Plus, it also becomes more difficult once you throw in activation quantization, because the left-hand side might be quantized as well, and it might be quantized in different ways, whether it's static, dynamic, per channel, per tensor, etc. And so I would need a custom op for all these combinations. Right now, this is the combination that it is most relevant, and so I think it's fine to have it as a sort of early optimization, but I don't think it's necessarily the best way to preserve it in the long term. And so I would like in the long term instead to have it separated into group-wise quantization operator, which is going to be custom, as well as then a standard matrix multiplication operator, and then leave it to the compiler to actually fuse them, since a compiler is also going to have much more infrastructure than I do within the quantizer to handle this kind of stuff. And so to wrap up, I would say a couple of things that I'm currently working on is one, right now, at least the compute after the quantization, so after weights are unpacked to a higher precision, is still assumed to be float 32. I would like to move to float 16, since that's what a lot of repositories are already doing. The annoying thing there is partly the issues around float 16 support for in PyTorch for CPU, in the sense that, for example, you cannot easily do tracing when you have float 16 operators, and so we need to work around that, as well as some numerical issues that are easier to encounter when you have a sort of more general implementation, when you overlay quantization on top of float 16 values. But I mean, it can be done. I'm working on that. The other thing is obviously to extend it to more model families. There's a lot of LLMs out there. They're all fairly similar. So usually it's just a matter of doing some coding changes to account for some specifics of how certain model structure might be different from others. So, but it's some work that needs to be done. And I'm always, always welcome PRs from anyone that is interested in contributing in that sense. And yeah, that's it from me. Hopefully it was useful enough, and let me know if you have any questions.
Well, I have a question. Thank you so much for the presentation. This was really interesting. So in the previous slide, you mentioned you can perform some of the quantization by just inserting torch ops, right? Like, I guess you replace the weights tensor with an int tensor, and you insert some torch ops in there to expand it. Is that good enough for getting will that always lead to performance benefits, or do you have to sort of hope that the compiler does the right thing with the torch ops?
Yeah, no, I do depend on the compiler making good choices. I would say the way that this typically works is that within the quantizer, at least the way that quantization is inserted, or at least the way that I do it, is by assuming I don't want to say ideal, but that I have a good enough compiler at the backend that is capable of performing the type of fusion that then unlocks the benefits of quantization. And so this is why I always choose my word carefully in saying that quantization enables potential speedups. It doesn't necessarily guarantee them, because it's doing 50% of the work in giving you, at the end of the day, good accuracy with small integer numbers. That's what I take care of. But then I do depend on the compiler to actually be able to understand the fact that the network is quantized and take advantage of that in a smart way. I try to have the compiler as much as possible by placing, doing quantization in a way that I know on paper at least can unlock these benefits, but then you do need an actual implementation to do that.
Makes sense. Yeah. Are there any other questions from people in the audience?
All right. Thank you, everyone.
Yeah. Thank you so much. Now, Sean, do you want to give us an update?
Hey, folks. Yeah, so I just wanted to give you some updates on the sort of top-level project leadership. First of all, I would like to just say how much of a huge success we're having, and the community is pretty much self-sustaining at this point. I mean, my involvement has been relatively minimal in terms of the top-level project steering for, I don't know, almost this whole year, I would say. And just like LLVM, which our community is modeled after, there's very little centralized guidance needed. We have code owners that determine the right thing for each of their sections, and that's it. And that's a huge success. I mean, the project is basically kind of does what it's meant to do, and we have some really good paths to scaling it to the future use cases it needs to address. So that's awesome. So with that being said, over the next couple months, I'll be ramping down personally to more of an emeritus status that, for example, Stella has been on up until recently, and then Stella will be ramping up out of her emeritus status just to make sure that the project has a top level owner in case something needs to be escalated. But like I said, we've been sort of operating effectively this way. The community has been very self-sustaining and not needed almost any steering for almost this whole year. So we don't really expect any changes to the project's trajectory or day-to-day operation. So in my opinion, this is really good news. I mean, this was our goal from the very beginning, is to just have a community watering hole, just like LLVM, where there's code owners and the code sort of lives how it is. People can come, contribute, own their own destiny. So yeah, thank you to all of you that have made this possible. I'm super excited to see the project continue to evolve and be used. And we're seeing all these things, like, I mean, Anush is talking about, like, VS Code plugins running Llama and things like that. And it's just like, it's amazing to see all the places where this is being used. So thank you everybody very much. And does anybody have any questions about this slide?
If there are no questions, I do want to thank Sean for all the guidance and leadership, and obviously Ramiro also, right? And we'll have Stella coming out of retirement, so we'll have someone. But Sean, I think feel free to always stop by and give us guidance. I think we can use the clean articulation of like architectural layering and all that that really help scale. And as we get, we're kind of in autopilot now, but as we get further, if there are any things, your feedback will always be welcome.
Yeah, and by all means, I mean, it's not like I'm disappearing off the face of the earth. Feel free to, to send me, ping me into bug reports or whatever. yeah, happy to help out.
Cool. Thank you.
All right, and that's all the update I had.
Awesome. Yeah, thank you so much, Sean. Yeah, I do want to echo the sentiment of Anush. You know, the success of this project has been in big part for the great setup that you were able to create in Torch-MLIR. So thank you for all of that.
Thank you. It means a lot to me.
Yeah. All right. So now the usual monthly checkup. So it's been really nice to see people from the community helping out with PRs, reviewing PRs, and people raising up issues whenever there's CI problems and things like that. So the community seems to be very self-sustaining, as Sean mentioned. But if you do have any issues, this is a good place to bring them up. Whether PRs are taking too long to get reviewed, or there's like things that are hard to debug in Torch-MLIR that could be improved. So if you do have any feedback, feel free to mention it now. Or you can also open a GitHub issue and do it that way. Awesome. No issues. Yeah, are there any other questions or topics that people want to discuss? All right. Well, thank you all so much for coming, and have a good rest of your week.